let's go ahead and dive in then. So, like I was talking about last time, right? We kind of had this picture of the way we should think about RLHF. It's a series of projections, and we can kind of think of offline and online algorithms as being different sorts of projections and such things, right? And that was really sort of the setup. Today is really, I think, more of the payoff, where I'm going to try and tell you why viewing this problem in that particular way is actually useful, and what it sort of lets us kind of do in terms of explaining a bunch of results people seem to see in practice. Also, who is scribing for today? Cool. Good luck as always. So we're going to try and answer 3 separate questions today. Interestingly enough, I think that people asked me at least the first 2 of these questions in lecture last time. So I'm curious if anyone will have the answers to them or they thought about them between. But the first thing we're going to try and talk about today is in the derivation we did at the end of class, this sort of DPO derivation, we made one really strong assumption. And I want to talk about what that assumption was and what happens when we break it. The next thing I want to talk about is when is the sort of like fancier 2-step procedure we talked about and the simpler 1-step procedure we talked about at the end equivalent. What this means is that when this is true, there's no reason to do this fancier, more complicated thing, right? This sort of simpler maximum likelihood estimation thing is all we need. And then a thing that's going to be kind of interesting is that from the perspective we talked about in class last time, it's going to turn out that these 2 things really should be equivalent. You really should see the thing where there's no reason to actually do this sort of fancier RL-based thing we talked about. But in practice, everyone actually does this fancier RLHF-based thing. So to sort of like close the kind of lecture, we're going to talk a little bit, I'm going to put on my sort of more implied hat. I'm going to talk about like what is actually going on under the hood and what actually sort of explains the discrepancy between the theory we talked about last time and the sort of practical reality of the situation. Before we get into too much of that though, let's do a recap of things. So we had talked a little bit about, a while back, about these things like forward KL, reverse KL, back when Drew was giving one of his lectures. So can anyone remind me, we talked about how a particular kind of algorithm is like minimizing the forward KL to the data. What is that? Three letters. You maximize the
Not likelihood.
Yes, right. So maximum likelihood estimation, right? So the sort of standard supervised learning thing kind of we always do in machine learning, right? And we talked about how this is really can be thought of as minimizing the forward KL to the data set you actually have collected in some sense, right? And then we had sort of talked about at the end of last class about how minimizing the reverse KL can really be thought of as the sort of softer L style thing. So just to sort of make sure we're all on the same page, when I say forward KL, what I mean is that the sort of data distribution Q here is fixed, and then we're optimizing this sort of thing P here. So the first argument to KL, right, is the thing that sort of tells us what we're taking the expectation over. And the way I've written it here, P is the thing we're always optimizing. So P here is the thing we're actually optimizing. So you'll notice that the data distribution here is fixed, and we're just sort of taking the P like match what we saw in the data, right? When people say reverse KL, what they mean is that you are actually choosing the distribution of data here, and that is affecting this sort of, we're trying to match this sort of thing here. So again, we're actually minimizing the P here. It's actually controlling what we're taking the expectation over in terms of the data set, and that also shows up over here. So this is sort of the, like I guess the sort of notational difference between these 2 things, right? Really P is the second argument here, it's the first argument here. But the distinction between these 2 actually matters more than it might seem at first. So let me give you an example of why I think knowing this actually matters. So let's say we had a data set or a data distribution that looked something like this. So it's this sort of bimodal distribution with 2 tuples. So this is a Q in the notation I'm using up here. And I'm going to give you two choices of P, so a distribution we could actually fit. So let's say P1 is going to look like this. So P1 is basically going to pick one of the modes and kind of forget about the other one. So you can think about this as being like a mixture of Gaussians. I'm asking you to fit with a single Gaussian. Then we're going to have another distribution here. I'm going to call it, so let's use a different color. I'm going to call it P2. And you'll notice here that I don't exactly get either of these two modes correct, but I do not like completely miss one of the modes, right? So it turns out that if I minimize forward KL, I'm going to pick one of these. And if I minimize reverse KL, I'm going to pick the other one. Does anybody have any intuition, or can anyone tell me, like, if I minimize forward KL, which of these two I would pick? So if that's a hard question, let's think about it a little bit more carefully together. So when we're minimizing this thing, right, the one thing we never want to do is have a situation where Q of x is really big and P of x is really small, right? Like think of P of x being 0, right? But then we're taking log of infinity, that's still infinity, still a big number, right? So if I ever have a situation where Q of x is non-zero, I never want to have a situation where P of x is 0, right? So this means I never want to actually have a situation where I don't cover something that's in the actual data. So between these two, which one will forward KL pick? Exactly. So forward KL is going to pick this guy. And this is why sometimes people will sometimes say forward KL has a mode covering behavior. Okay, now by process of elimination, you can say that reverse KL is going to pick the other one, right? So we call this mode seeking, in the sense that it's just going to pick one of the two modes. People will sometimes also call this like mode selection of a kind. The way you can try and back this out from the math here, right, is that if I look at this ratio, right, if Q of x is like something kind of big, like it's this peak over here, I want to make sure I don't pick a P of x that's really small, or else things will not go well. So, but you'll notice that I am never dividing by like the data distribution in a way that would cause a problem. So I'm okay like actually not covering one of the modes. So maybe the sort of connection to what we talked about last time is that when we think about sort of reverse KL things, right? Really what they're going to do is if you can't pick both of the modes, you're really going to pick one of them, right? And, oh, yes.
Oh, yeah, I have a question about reverse KL. I guess there's still a constraint on the probability distribution, right? So this is sum to 1. And if the green distribution, true distribution also sums to 1, it seems like it would be impossible to fit to a single mode, right? So then, like I understand if since we're controlling the sampling distribution, it makes sense that we would try it, but you could even, try to fit to a single sample, but you don't do it because then there's a really large gap between the actual value of P and Q. So how, I guess in reality there is a gap between the probabilities, right? So
Yeah.
how do you explain that?
100%. So the way I think about this is we have some data distribution, Q, right, that can come from wherever. Here it's like 2 Gaussians. And then we have some family of distribution, in this case, unimodal Gaussians, that I can kind of select over. So basically, let's say I get to pick the mean and the variance, right? Just 2 parameters. And to your point, by just picking that mean and that variance, I can't exactly fit this distribution. I'm not in like the realizable setting. There's no thing in my class that can actually exactly fit this thing. But if I have to pick a kind of a recurring theme in this class, right, is if I have to make a trade-off, right, I have to choose something, it's like what kind of trade-off do I want to make, right? And what we're saying is that if you try to minimize forward KL, do the sort of maximum likelihood estimation thing, you'll say, okay, even though I can't really get both of these modes correctly, I'm going to blow up the variance, so I end up covering everything. Versus for the reverse KL, right, what I'm going to do is I'm gonna say, okay, well, as long as I get one of the modes perfectly, that's fine. That's all I really care about. Make sense? Good. Other questions? Okay. So I think the thing that is kind of interesting to think about then is why in things like RLHF we actually care about mode selection versus mode coverage. I don't think there's a particularly strong reason why this is true, but basically think about something like, I don't know, your language model can basically only generate text from either English or French, right? You'd rather have your language model generate English correctly than sort of switch between English and French midway through a paragraph, right? So it's like if you can only do one thing, you should choose to just do one thing well. I think that's sort of just a thing people want when they're designing these sorts of systems. So let's maybe bring back in the picture we had last time. All right, so I guess to emphasize that point, forward KL is mode covering and reverse KL is mode seeking. So we had this picture last time of the way we think about these algorithms, right? Where we have a data set D being some point in space, we have some class of word models R, and we have some class of policies pi. So can anyone remind me what this sort of two-stage RLHF procedure looks like? Like what's the first step? Yes. So we're going to do forward KL from D to what? R. Right. So we want to fit a reward model, right? So we're going to say, okay, I'm going to do some sort of maximum likelihood estimation, aka supervised learning, to fit a reward model R. And like you just said, this is going to be under this sort of forward KL metric. Yes. Okay. Now, what is the second step?
First, you have to buy.
Okay. So the second step is going to be, we're going to go from this reward model, and we're going to fit a, oops, that did not come out well. We're going to try and fit a policy here. So pi hat RLHF is going to be a reverse KL projection. And we had talked a little bit about how this is really just like a logistic regression style thing, and how this is the sort of like soft RL flavor of things. Okay, cool. So 2 stages, doing one projection here, then another projection here. Can anyone remind me what the one-step procedure looks like?
Directly mapping to policy space.
Right, under what metric?
The MLE.
Yes, right, exactly. And MLE corresponds to forward KL, right? Good. So what we're going to do is we're going to map from here to the space of policies, pi, and we're going to get some maximum likelihood estimate here, and that's going to be under this sort of forward KL metric we talked about. So the sort of question I really want to focus on today is, okay, at the end of the day, we want a policy, right? At the end of the day, I have to give you something that generates a language that actually does the task, right? If that's true, the fact that we're taking a detour through a word model, that we have this 2-step procedure, I think you need to justify it very clearly why there's actually the use of this complexity. There's a use in doing all this sort of stuff. So most of the lecture today is really going to be on why we need this sort of extra complexity. I'm going to write this in slightly more formal notation now, but this is really just recapping what we just built together, that we can really think of things that look like the offline algorithms, DPO, direct preference optimization, basically doing some sort of logistic regression over a policy class pi. We can think of reward modeling, basically is doing logistic regression over our reward model class R. And then we can think of this sort of soft RL step as doing this particular sort of soft RL thing where we say, okay, I want you to pick a policy pi that maximizes the scores my reward model gives me, while not straying too far in terms of reverse scale from my reference policy. So we just talked a little bit about, what are the sort of properties of reverse KL, right? That, we want to do mode selection rather than mode coverage. And this will sort of come back to us in a second. Okay. So before I give you the answer, did anyone have a chance to think about what really strong assumption we made in the DPO derivation? It's kind of subtle. It took us a really long time to figure this one out, but I'll be very impressed if anyone thought it through. Going once, going twice, going thrice. Okay. Turns out that really boils down to we were essentially assuming full coverage of our preference data set, in the sense that we see every possible completion to a prompt compared to every other completion to a prompt. And turns out without full coverage, you basically can't control the reverse scale, right? Because if you remember, this guy right here, right, involves an expectation over trajectories sampled from the policy, right? So unless all things in that distribution are covered by my data set, there's no way I could actually say this one is actually small, right? So I'm going to give you guys a sort of toy example of this in practice, and then we'll kind of go to slightly more complicated things. So let's say we think of the following kind of relatively simple problem, where basically you can only pick between 3 different completions to a prompt, right? Just Psi1, Psi2, and Psi3. And let's say our reference policy basically gives you a uniform distribution over Psi1 and Psi2. So it picks between these two with equal probability. Let's say we generate a bunch of data like this, and then we ask our person. Once again, you can tell from this little thinking wheel, they're thinking very hard. We can think about like, okay, maybe they tell us, okay, I always prefer Psi1, I always prefer this way to complete the prompt to Psi2. So I'm gonna box this guy in red, and I'm gonna box this guy in green. So let's think about what our sort of RLHF procedure is gonna do now, right? The 2-stage one. So first, when we fit this reward model, right? Because we're always saying Psi1 is better than Psi2, I'm going to always give a really high reward for Psi1 and a relatively low reward for Psi2, right? So I'm going to get something like 1, 0, and then the sort of critical part is, do I have any information about what I should set Psi3 to be here? No, right? So who knows what it's going to do, right? So we could set an arbitrarily high value, something that's terrible there, right? I'm just going to put a question mark there. Now, here's a question. Let's say I got a value here that was super high. Let's say it was like 10. So the reward model is really extrapolating poorly out of distribution. And now I think about solving this problem, right? If I put any probability mass on Psi3 here, what does this term become? Infinity, exactly, right? Because this term basically says it divides by 0 for Psi3, right? There's no probability mass in the reference policy. So even though my reward model might extrapolate poorly out of distribution, because I have this additional KL kind of term tacking on, right? I'm going to say, oh, you should never, ever play something out of distribution. So you'll get a policy that looks something like, I'm always going to play Psi1, I'm never going to play Psi2, and I'm never going to play Psi3, right? So basically, when I talked about how we can really think of RLHF as mode selection, I basically look at the behaviors my reference model has, and I select the one that's better. Okay. So now let's think about the DPO loss here, right? One of the nice parts about lecturing with a screen this big is normally I can't have equations this small. So you got to appreciate the small things in life, right? So let's think about this data set here, right? So this data set is just going to be Psi1 and Psi2, right? Because that's the only 2 things we ever saw. So basically, it's always going to just look like Psi1 is preferred to Psi2. So all the pluses here are going to map to Psi1, all the minuses are going to map to Psi2. So, okay. And the other thing that's interesting is the reference policy puts equal weight on these two things, right? So what that means is that these two terms actually cancel, right? Because they're exactly the same. Okay, so I want to maximize the difference in probabilities between these two, between psi1 and psi2, right? Or really their log ratio. So one way I can do that is I can put all the probability mass on psi1 and no probability mass on psi2, no probability mass on psi3, right? Because then the ratio of log of 1 over 0 is infinity, and I'm doing an argmax here, right? So that's good. Okay, now for a slightly more subtle question. What about this? Let's say instead what I do is I set this to be 0.1, I set this to still be 0, I set this to be 0.9. Is this okay? Does this minimize this loss? Yes, why?
I mean, still the ratio of psi1 to psi2 is still, I mean, tends to infinity.
Exactly, right? So all my DPO loss here, right, doesn't actually ever look at psi3, right? So I can set whatever value I want here as long as this ratio is sort of, the ratio is infinity, right? This means that I can sort of, I don't get the sort of extra correction here I get because I have this extra KL thing tacked on here, right? So while learning from an offline Emily thing, right, both the word model and the policy might extrapolate poorly out of distribution. When I put this extra KL thing on, I basically can quite correct for that post hoc. That's sort of what the benefit of interaction here is. So put a bit differently, really what happens is DPO doesn't regularize the reference policy correctly. Doesn't actually control this reverse KL. And this means you can kind of produce out of distribution responses, right? And the reason this is bad, right, is that like if I start generating text I've never gotten human feedback on, I have no idea whether this is really bad or really good, right? Maybe psi3 here is just generating a bunch of swear words or something, right? Like maybe we don't want our model to do that, but I have no way to actually control that from happening. So I think that the way to think about this is when we were actually saying that minimizing this actually gives you the same solution as the whole reverse KL thing, right? We were essentially assuming that this involves seeing all pairs of trajectories. So you can actually get this sort of global minimizer. Does that make sense? Cool. Any questions about this point before we move on? So now let's go on to a question that someone asked last time, which was that, okay, I've told you that with coverage, things are different, things can break. But when are these two things actually going to be the same, right? So it's a bit subtle, but I'm going to give you guys sort of an intuitive version of it, and then I'm going to give you sort of a proof of this. And the reason we care about this thing in the first place, right, is because if these two are equivalent, then there's no reason to do this fancy thing, right? There's no reason for people to be spending millions upon millions of dollars on their training run. And it's going to boil down to basically the following. When the set of policies pi and the set of reward models are isomorphic, meaning that they cover the same set of functions, and all projections, the forward KL, the reverse KL, both of these things, are exact, since I get the exact point I want to meet. I don't kind of have an optimization error. So I think this claim sounds kind of fancy when I write it out this way, but I think it's actually a very intuitive claim, and I think you might be able to see it pretty clearly from the picture. Right, so essentially what I'm asking is, when is the picture like this? That this extra projection basically gets you to the same point as you get from MLE. And it boils down to something I think is actually relatively simple, right? Maybe before I say it, does anyone have an intuition for why, if these two things are true, these two sort of thing you get out of the two-stage and the one-stage thing must be the same? Yeah.
I think the only case where you get a better policy is when the reward somehow generalizes beyond the input set, so you have new interactions with more signal. But if this holds true, then and they cover the same functions, then there's no new information basically.
Yeah.
So there's no, but that's it, yeah, I don't know more.
No, I mean, that's entirely correct. You know plenty. In a slightly more formal way, right? If basically these two things are isomorphic, right? That means that r hat Emily and pi hat Emily are basically the same point, right? Because I'm minimizing the same like objective over the same function class. So I have to get the same point. And then if the secondary projection is perfect, right? This means I basically don't move you, right? So it's like the first step basically gets you to the right answer, and the second step doesn't change where you are. Therefore, end to end, you must end up in the same position as the first place. I'm going to state this a little bit more formally in terms of the math now, but does the intuition here make sense? Good. So, I think we have time for this, okay? So, I'm going to say that when the classes are isomorphic, the following condition holds true, which is that the expectation over the sort of gloss of our data set here of over policies is going to be the same as we would get if we did over words. Hopefully this is somewhat intuitively true. Can anyone tell me why this should be true? So let's say I had some function f, and the only three values I can put into f are 1, 2, and 3. And I tell you, okay, my class 1 is 1, 2, 3, and my class 2 is 3, 2, 1. If I minimize f over both of these two classes, do you see why it must give you the same answer? Because I'm minimizing the same thing over the same domain, right? And when we have these two classes be the same, what it means is that basically the sort of log sum you get from the policies and the kind of just the trajectory level score you get from the reward must be the same. And if these two functions are the same, their losses must be the same as well, right? So really, this is going to be saying it's minimizing the same function over the same class. So for the next step of this proof, I'm going to be a bit hand-wavy because I don't want to state it too formally. But basically, I'm going to assume that the minimizer in both of these classes is unique. Therefore, these two functions, pi hat MLE, or the log sum of it, and the reward model here must be the same. So basically, assuming uniqueness of minimizers, I can basically say that on whatever trajectory I pick, these two must have the same value. The reason I'm being a little bit picky about uniqueness of minimizers, right, is like think about how here, because I'm looking at a difference across trajectories, I could just like add a 10 to this and I'd get the same loss, right? So you can state this more generally if you basically think of the set of minimizers, but just for simplicity, if that's hard, just think about having a single unique minimizer. And then if these two have the same value and there's only one thing that gives me that minimal value, these two must actually be the same thing. Yeah.
Does this use the, I guess, assumption or definition you stated last time that the output pi is sigmoid of the reward? Because that's basically like the first line is basically that definition you mentioned last class.
Yeah,
I think.
yes.
Yeah.
Yeah, exactly, right?
Okay.
So, like Bart is saying, we can really think of this as being R. I apologize for like how many subscripts there are in the notation, but this is really the R we get from the log ratio. Yeah, exactly. Good. Does that make sense? So I basically said these two are the same object, right? Now the proof actually is like relatively clean. So we can write RLHF out at this as this sort of reverse KL projection, right? Like what we had said was basically that this sort of, the minimize the reward plus the KL basically looks like taking the optimal thing for this R hat thing, the X of R hat thing, and doing a reverse KL projection onto the set of policies. This is really just sort of by definition as soft RL is an RKL projection. Now the sort of like clean thing here, right, is I've basically said that r hat here and pi hat here are the same thing, right? So this means I can just plug in r hat pi here instead, right? Because these two are the same function. Then maybe to complete the proof, I'm just going to note that the thing that minimizes this KL over this class is actually going to be the maximum likelihood policy. Can anyone tell me why this must be true? Like, why can't it be some other policy?
You assume the projection. Yeah, you got, yeah.
They're equivalent classes, so I mean, everything should have a unique projection on the other.
Yes, that's one part of it. There's one other part I'm looking for, though. All right, you two.
No, I'll say.
I thought one of the assumptions was there's an exact projection, but that's kind of the same what he was saying.
Yeah, okay, so exact projection is correct, but I think the thing that I'm looking for, a little bit simpler here, is that, okay, so there's 2 points here that are important. The first is that, okay, we talked about how from the DPO derivation, right, the sort of optimal policy for r pi hat is pi hat, right? So it's going to actually be that pi hat, right? And then the other thing is that we actually know that pi hat MLE is in this big class, big pi. We actually can minimize the projection because, like, sort of by construction, we picked a point that's already inside the class. So really, this is just coming through because pi hat MLE must be in this class, big pi. So I'm not going to go into this interpretation too much, but if you've taken a statistics class before, what I'm really stating here is a sort of more, in more math, basically the idea that maximum likelihood estimation is invariant to reparameterization. So what that means is that even if I think of like doing a thing over word classes and policy classes, as long as these cover the same set of functions, I must always have the same answer that comes out of it. Don't worry too much if this is not a thing you've seen before, but I think it's just a nice interpretation of what I'm actually saying here. The last thing I'll note, because it shows up on your homework, is that we had mentioned this thing about natural policy gradient being covariant, right? So covariant and invariant are basically terms, I think, from statistical physics. The connection is basically that MLE being invariant to reparameterization means I always get the same point when I actually solve the optimization problem the same way. Natural policy gradient being covariant means that no matter how I parameterize, I end up taking the same step. So covariance really here boils down to the sort of like direction of the step you're taking. You end up at the same point, versus this is saying over the whole optimization process, I will get the same answer. This is again like a fairly subtle point, and I don't want to belabor it too much, but it is sort of, there is a slight nuance between these two things. Okay. So I want to maybe make one other point, which is that, okay, this is a bunch of math. It's kind of nice. Maybe it's pretty to look at for some people. I think the natural question you should have whenever anyone does proof for you is like, why should I care about this result, right? Like, why does this actually matter? And I kind of want to go back to what we were talking about last time, where we had these sort of like policies and rewards, right? And we'd said that when we had these sort of isomorphic classes, everything gives us the same answer, right? The thing that's kind of interesting in practice is that you actually do have isomorphic classes in practice. When you look at the way people actually train these language models, when they're training word models or policies, basically what they do is they do supervised fine-tuning, SFT, right? And then they basically fine-tune both policies and word models from the same checkpoint. So all they do is they basically, for a policy, right, it's like some kind of, thing, and then they stick it into a softmax to actually get a distribution over tokens. All you do for a word model is you basically get rid of the softmax, and you basically stick in one extra linear projection layer. So like one linear transformation, which doesn't really matter, I think. These two really are the same function class. And you are optimizing them from the same SFT checkpoint. So you're basically starting from the same point, you're optimizing over the same function class. And like we talked about, we're basically doing logistic regression for both of these, right? So if you have two like optimization problems, I should say, where you start at the same point. You search over the same space using the same loss function. It's really weird to think that you must get two different answers, right? So this is where things get kind of interesting, and this is why this is my favorite thing I've worked on my PhD, because it took me a really, really long time to actually figure out what was going on here. But I want to maybe, I don't know how to phrase it in a way that doesn't sound strange, but hopefully it's understandable what the confusion here is, right? That we're saying that we see something where we actually are in the setting we just talked about in theory, in the sort of isomorphic classes setting, in the sort of situations we see in practice, but we very robustly will actually see a difference in performance. And then we'll spend the rest of the lecture today talking about what the sort of more fundamental reason there really is a difference. Does that kind of overall picture make sense? Cool. Any questions about that before we kind of dive into what's going on under the hood? Yeah.
When we're talking about the practical manifestation of this theoretical, like maybe I'm not understanding this correctly, but how are we negating optimization error?
Yeah, that's a good question. So it'll maybe get a little bit more clear when I go through the example I'm thinking of, but I'm basically going to use the same optimization algorithm for both the online and the offline things. So while you can't get the error to 0, it has to be like equally bad, and that's enough, I think. Yeah, that's a very good question. Does everyone understand why that question is interesting? It's because, like, sort of in the proof I just gave, I just argued that I have to have perfect optimization to the projections perfectly. But it turns out that I think in practice you can't say everything is kind of perfect, but you can say it's equally bad. And then that still begs the same question. Cool. Okay. So, I thought it'd be kind of fun. So normally I feel like when I do this sort of stuff, right, I give you the answer and then we talk about the answer. I thought it'd be more fun this time if I don't give you the answer and we get to come up with the answer together. That's why there's no kind of blue thing in there. So first let me give you some evidence that there really is a difference between this two-stage thing and the one-stage thing, right? So these are probably the two most canonical RLHF papers, the ones that people cite have like citations at this point. One of these is by the Anthropic folks, one of these is by the OpenAI folks, right? And what you'll see is that like when they do their sort of offline fine-tuning procedures, you basically get some performance. So the x-axis here is how big the model is, so they're trying to do like a scaling law thing here. The y-axis here is how often, when you asked a person, how much people preferred what the model said to like a ground truth thing a person said. They're saying, okay, I have some article, I want you to summarize it, I ask the model to summarize it, I ask some like person summarize it, and I then ask other people, okay, when do you prefer what the model said to what the person said? So being able to get above this sort of 50% is actually very impressive. You're kind of getting like superhuman performance in some sense. And what you'll see is that when you do this sort of offline things, right, you basically can get close. You can like, with a really big model, 175 billion parameters, crazy, you basically can just touch this sort of human level performance. But really to kind of go beyond, you need this sort of RL step. So all the kind of stuff we're talking about here is all done via reinforcement learning, the sort of two-stage procedure we had talked about earlier. So hopefully this is at least some evidence that like, okay, there seems to be a benefit of doing this whole two-stage thing, even though we said in theory there doesn't appear to be one. And maybe the other thing I want to note here is kind of bringing back our meme from last time, right? That like, it's not just like OpenAI who's doing this. Like the Gemini folks at Google are doing this. The DeepSeek folks are also doing this, right? Everyone is doing this sort of more complicated two-stage thing. And as well, some of you are probably realizing for your course projects, right? Getting RL to work on language models is extremely annoying and takes a lot of time. So it's not like people are doing this because they thought it'd be more fun to do it this way, right? There has to be some like more deep fundamental underlying reason why all this sort of complexity, this sort of two-stage process is actually necessary. So we're not going to talk about that, but hopefully everyone kind of believes me that, you know, in practice people really are doing this more complicated thing. So, you know, I don't have the compute to train a 175 billion parameter language model. I'd be really impressed if any of you do. Let me know. We could probably found a startup or something. But I'm going to try and give you a set of experiments that are sort of closer to what we can actually do in academia. and sort of show you that we still see this gap show up. And then we're going to try and do real science and try to explain why this gap actually shows up. So I'm going to pick a particular task, which is going to be summarizing some Reddit posts. So basically, we're going to get, a bunch of posts scraped from some subreddit. We're going to ask, I guess, some sort of SFT model to basically generate multiple summaries of how to summarize a Reddit post. And then we're going to ask a person, okay, which of these two summaries do you prefer? And this is going to give us that preference data set D, that kind of point in the middle we were talking about earlier. And then sort of to reiterate some of the points we talked about earlier, we're going to use the same data set to train both the policies and the reward models. So both the policy and the reward models, the two-stage thing and the one-stage thing, both see the same ground truth human preference data. So everyone sees the same data. We're also going to start from the same SAP checkpoint to train both. This is going to be like the sort of isomorphic classes setting we just talked about. So we have the same data set, we start from the same point, and we are fine-tuning the same class of models. And then the last thing I'm going to do, and this is sort of related to your question, is I'm going to use the same optimizer for everything here, just to sort of eliminate another confounder. Sometimes when people write papers about this stuff, they use different optimizers for the online and the offline algorithm, and then you can't eliminate the confounder that it really is because of optimization error. So offline DPO is the thing we talked about, right? I just give you a data set. Online DPO is a bit different. So what I mean by online DPO is the following. Basically, for some plot, I basically sample a bunch from my policy. Let's say I sample, I don't know, like 25 ways to summarize a Reddit post. Then what I do is I rank those samples via my reward model. So I say, okay, give me an order over these of which completions to prompt, which summaries you like more than the other ones. Then what I do is I take the one that's the highest on that list, okay, the one the reward model liked the most, and the one that's the lowest on that list, the one the reward model liked the least, and basically use that to construct a new preference data set. And then I just plug that into DPO. So basically, I'm constructing an on-policy preference data set by basically using my reward model to rank the completions from my policy. Does that make sense? Is any part of that confusing? So when I say I'm using the same optimizer, what I mean is I'm basically plugging things into the same loss function. The only thing that's changing is this data set is actually some on-policy thing that was generated by sampling from my policy, and the labels are generated via this reward model, not sort of ground truth human feedback. Okay. So it turns out that this sort of gap, the one we see these sort of like large-scale systems people actually use in practice, actually shows up even on the sort of like relatively tiny experiments I can do in academia. Fun fact, someone actually in this course was on the paper that created the sort of models I was fine-tuning for this, which was actually really cool. But let me sort of break down the sort of plot we have here, right? So the y-axis here is going to be basically the win rate against human reference summaries. So I'm gonna have some I'm gonna fine-tune my model in some way. I'm gonna have some validation set of prompts I haven't seen before. I'm gonna say, okay, complete the thing, summarize the text in some way. And then I'm going to have a person do the same thing. And then we're gonna, here because I don't have the money to pay people to judge completions of the prompts, we're basically gonna query some really powerful model, in this case GPT-4o, to say, okay, which of these did you prefer? What the human said or what my model said? We're going to do this across two sizes of models. We're using this sort of family from the Pythia models. That doesn't matter too much here. Similar things hold more generally. And we're going to do it across 1.4 billion parameters and 2.8 billion parameters. Now let's talk about what's actually in the plots. So this sort of initialization, our reference policy, right, is going to be the SFT thing here. And you'll see it gives you something. It's not terrible, but it's only wins a fourth of the time. It's not particularly good. When you run an iteration of DPO on this preference data set, you'll jump up to 50%, at least on the smaller side. And that's okay, that's an improvement. We're learning from preferences, right? That makes sense. You can try running another epoch of DPO on the same data set, right? So just kind of shuffle the data, look at all of it again. And you'll get a slightly higher score. What you'll notice is that the on-policy algorithms, these two here, both do better. So the difference here is, here what I did is I started from the SFT policy. I sampled from it, I ranked the completions on their word model, made that thing, and then I did one iteration of DPO on that to get this here. So what this is saying is that even when I start from the same policy, on-policy feedback is helping over an off-policy thing. The thing that we found kind of surprising and is actually really interesting is I can take the output of DPO and run an iteration of online DPO on top of that. What I can do is I can take the policy I learned from DPO, I can generate from it, I can rank those samples with the word model, and run another iteration of DPO. And what's kind of interesting is that I can actually still improve the performance of DPO with the word model, right? And this should be kind of strange to you, right? Like I've trained two things, a policy and a word model, on the same data set, over the same function class, with the same optimizer. And somehow I can squeeze more out of the word model on top of what I already squeezed out of the policy. So I remember when that happened, we were like, well, that's kind of crazy. It took a little bit more compute to do this, but you can also do this for slightly larger models, and you'll again see this sort of difference. So the point here to take away, I would say, is just that like you see a sort of robust gap between online and offline algorithms here, even in this sort of isomorphic classes setting we just talked about in theory. And you can kind of, there's like more juice to squeeze out of the reward model in some sense, which is like kind of interesting. Any questions about those results before we dive into what's going on with the hood? Good, okay, everyone's convinced. You guys are much more easily convinced than most people on Twitter. Okay, so when, Drew, Steven, so everyone who has or will give a lecture for this class, so Drew, me, Steven, Wen, and Zanderban were thinking about this. We came up with like 6 hypotheses for why there could be a gap here. I'm not going to go through all 6 of them because that would be a little bit exhausting. But I like to talk about a few that I find the most kind of interesting and what I've seen people say the most in prior work. Before we do that, though, I'm curious, does anyone have any guesses for why there could be a difference here?
The reward calibration, like it's, for the online policy, the rewards that you get from the RM are just more reliable because they're closer to what the model is going to generate or see at test time as well. I don't know what the right language to express this. I didn't find it surprising that the online algo is doing better than the offline algo. I do not understand why that was surprising.
Yeah. That's a good point. That's going to be the first hypothesis we had. I will get to that in a second. That is a good other ones. I'll be really impressed if we can hit all 6. There's no need to be like, there's no like dumb answers here, right? Any others?
Wouldn't we ensure that the reward and the policy classes are equivalent?
Okay, so another thing could be like, hey, maybe these things are like actually not super equivalent and there actually are, there's like a meaningful difference between them. I'm going to say for the particular set of experience we're doing here, I don't think that's true. They're around as close as one could hope for. But I think you're bringing up a good point in the sense that sometimes when people have done experiments of this flavor, they've used different classes for the reward and the policy. And in which case, like, yeah, I think it really could just boil down to the point that like, hey, maybe you have a smaller word model class, maybe it's easier to learn, something like this, right? So I don't think it explains the results I just showed, but it is a thing that can happen. Any other hypotheses? Yeah?
Yeah, this is a very tough question. But it seems like the online step can also help diversify the output distribution that I could learn. Like if you're just doing offline like optimization, you're always going to be limited by the data distribution that you began with. So probably just increase coverage or increasing the non-linearity in like the policy that you can learn using this extra step of the online.
Yeah. So I think that's very related to the first thing you brought up, that in some sense it feels like, okay, when I'm sampling for my policy, I'm getting access to new information, right? I'm seeing new things, right? Okay, so I'm going to still bucket that under H1. Any other guesses?
ensuring that the reward model is accurate on the samples generated by the policy? I mean, though we are training it on the offline data set, I mean, how couldn't there be a mismatch between the one that we are generating and the offline data set?
It could be. We'll talk about that more as well. That is part of the story as well. Okay. So even if you're too shy to say it, I hope you thought a little bit about why this might be true. And now let's talk a little bit about what at least some of the explanations are and why I think we can actually reasonably clearly refute them with the set of experiments we just did. So the first answer everyone kind of comes to when they think about this question, which I think is very reasonable, is that there's some sort of intrinsic value on policy feedback, right? I get to actually see what my model does, and I get to say, okay, I give you feedback on what it actually did. Right? And this seems kind of true, right? We spent a bunch of time in this class talking about how there's these separations between offline and online algorithms, right? For something like behavior cloning, right? Maybe I don't know what to do out of distribution, but I'm able to correct back to what I see before, things like this, right? So there's two reasons I think this explanation doesn't hold water here. I'm going to give you the first one, and then I'm going to give you what I think is the more subtle one. So kind of like the point you were making, I don't actually get access to a ground truth reward function here, right? All my reward labels here are just imputed via my reward model. So it's not like a usual separation between online and offline, or all the sort of things like, let's say, like we've been talking about in this lecture, because I don't actually get any new ground truth human preferences when I'm trying things out, right? So a bit more explicitly, all the on-policy labels are just made up, right? They're just some random number in my reward model spat out. There's no reason they actually have to be any better than the sort of things that are actually in the preference data set. They could be complete nonsense for what we know, right? And then you have to basically make it a thing that's relative, right? You say, okay, is it better for the reward model than for the policy, right? But this is generated by a word model that was trained on the same data set as the policy, right? So it's kind of prima facie kind of unreasonable to say that this was going to give you sort of some kind of better feedback, I think. And the other thing, this is sort of a subtle point, but we really can't create any new information when we're sampling from our policy, right? So think about it this way, right? Like, from like an information theoretic perspective, once I've given you the reward model, I'm sort of done, right? In the sense that like, all that's left is computation to turn that into a policy. I've told you how much every trajectory is worth. Now I just have to kind of, do the sort of computation thing, right? Like, technically, rather than doing this whole fancy PPO kind of RLHF thing, I could run the sort of tabular value iteration procedures we talked about earlier in this course to compute the optimal policy, right? This is literally a tabular problem. Now, of course, it'd be extremely computationally expensive and no one will actually want to do this. But technically, I don't need any on-policy feedback to solve this problem, right? I can literally do value iteration here. So there's no sort of like intrinsic value in on-policy feedback here. A particularly memorable way some faculty at Cornell put it, which I really liked, was that like essentially sometimes people seem to think of reward models as basically perpetual data generating machines, right? Like that somehow I fit this reward model, I can plug in whatever I want for my policy to it, and I somehow get like reliable feedback, right? But there's no free lunch here, right? You only really get what you put into the reward model. You only really get what you saw in the preference data. There's nothing special there. So I think the other reason I don't think this is true is that when we talked about things for imitation, right, we had said the real value of on-policy feedback is that it shows you how to recover from mistakes, right? Like, we said behavior cloning basically can't tie break well out of distribution, right? And you might think about the example we just went through for DPO, where basically DPO can put arbitrarily high probability mass on this thing that was out of distribution. And you might say, okay, this is kind of the same thing. We basically can't tie break on data we didn't see. It's a bit of a subtle point, but the reason I don't think this is the real explanation here is that I don't really understand how you can recover for language, right? In the sense that, like, let's say I generate a bad token, right? I generate like a swear word or something I'm not allowed to say. That's there forever, right? I have append-only dynamics. I can't just like forget a mistake I made in the past, right? It's not like I go a little bit off the center of the lane and I correct back, I can recover in that sense. In language, you can't recover. So I think that like maybe you can argue that, okay, the pre-training filters out all really bad things and you can try to make a more complicated argument, but ignoring sort of some of the details of that, does it make sense that like basically you don't get a sort of naive recovery thing because all I can do is append tokens, I can't get rid of information. I can't sort of forget mistakes I made in the past. Yeah.
Kind of recovery in some cases, like if you're like solving a math problem
Yeah.
and you say something wrong, you can say like, well, actually that was wrong, and then append like new tokens.
Yeah, that's a really good question. So when you're doing like chain of thought reasoning, I don't really care about any mistakes you make in the chain of thought. I only care about the final answer you get. So the problem is recoverable in that sense. But for generating text, I actually do care about the text you generated, right? Like if I said something to you and I was like, JK, that was actually totally wrong, you'd probably be like, why did you'd be kind of annoyed, right? So chain of thought and sort of reasoning things actually are recoverable problems. So like the big thing that like Drew, Steven, and I are working on now is basically generalizing this argument to the recoverable setting for reasoning. But yeah, so for this particular setting, no, but yeah, that's a really good question. Others? Okay, so hopefully people believe me that it's not just some sort of magic in interaction or magic in on-policy nest that's giving us, right? B, because we can't recover. A, because we can't create any new information, we can't actually get we get nothing new in some sense when we're sampling the policy. Good. I also note that this point I'm making here about not being able to create any new information. If you've heard of the data processing inequality in like an information theory course, that's basically a fancier version of what I'm saying here. That basically, once I have the policy once I have the word model, I can only lose information when I go from data to the word model. I can't create any new information, right? I'm not getting any ground truth human preferences after that point, right? So I can't see anything new. I'm not going to make this more formal, but that is under the hood what the kind of underlying mathematical reason here is. Okay, so one hypothesis, hopefully reasonably eliminated. Okay, so let's think about another hypothesis. Which is going to be some sort of failure to, that the offline algorithms fail to regularize the PyRef, right? We just talked about how if you generate all these sort of out of distribution answers, this can lead to kind of poor things because you've never gotten feedback on this stuff before, right? So I think the simplest way to see this, right, kind of bringing back the sort of two-term objective here that is very informal, but hopefully you believe me that it's roughly correct, is that reverse KL, right? Like we just talked about, has an expectation over trajectories drawn from the policy, right? And unless like D covers everything the policy does, it's not reasonable for me to expect that this is going to be bounded, right? This is basically the argument we went through in the first part of the lecture. So I don't think that explanation explains the results I just showed you. Can anyone tell me why?
You saw an increase in performance with just one epoch of online iteration, like in the last set on DPO one. So yeah, even though that may have like had very limited coverage, you did end up seeing an improvement essentially in the optimal policy.
Yeah. So I'm going to rephrase what you said a bit differently, but notice that I did not actually KL regularize correctly in any of the experiments I did, right? Like I used DPO for everything. So yeah, I'm DPO doesn't, offline DPO doesn't regularize the reference policy correctly, but neither does the online algorithm I came up with, right? All these things are equally bad in this sense. So, but definitely, I used the same regularizer for all the experiments, right? I actually didn't do proper on-policy KL regularization for anything here. So, yes, this is a thing that matters, right? You can get these sort of out-of-distribution results when you don't do this correctly, but it's not the highest order bit. in some sense, it's like a thing that matters, but it's not the thing that you should care about the most. Because I've just given you results where I remove this factor, I do experiments that eliminate this confounder, and I still see a robust difference in performance. I'll note, just to do a shameless plug, Yuda has a really nice paper on this that is linked on the course website, where he basically took the DPO algorithm and basically added a proper KL regularizer to it. Like we talked about how this KL regularizer, right, is just sampling from your policy and calculating a log ratio. So you can do that without any extra preference data and just tack that onto the DPO loss without any, kind of extra complexity. And it helps. It helps, but it does not close the gap to these real on-policy algorithms where you actually train a reward model and do the whole two-stage thing. So I guess what I would say is like, yes, I think this matters. We gave you a crisp theoretical example of why this matters kind of earlier on, right? This sort of 3-point thing. But turns out in practice, this is not like the highest order bit. This isn't the thing that matters the most. Does that make sense? Any questions about that point? Good. Okay. So, sorry, I thought I heard a question. Okay. So maybe the next one that people come up with is that reward models, in some sense, generalize better out of distribution, right? That in some sense, my reward model generalizes a bit better, and this means that I am able to, get kind of useful feedback. So if this is true, if this hypothesis is true, can anyone tell me why it would be reasonable to believe things work better for the on-policy algorithm?
So at that point, you have more signal, like more rewards data sets. But I think it's assuming that there's an inductive bias in your reward model that is aligned with the gradual reward.
Yeah, right.
So I'm not sure, some smoothness or something.
Yeah. So right, I'm being a bit hand-wavy about the reason why that might be true. But agreed that, yes, let's say for smoothness or some other reason, right, something about our reward model class is kind of special. And what this means is that you get this sort of you get kind of better feedback out of distribution than you do just in your preference data set. Somehow I learned to generalize beyond the training data, right? And the thing is that's actually fairly interesting in practice is this is actually true. You actually fairly reliably will see reward models generalize better out of distribution than policies trained via something like DPO. So the way I'm going to measure out of distribution generalization is the following. I'm basically going to do best event from a policy that is different than what was used to train these models. I'm going to use these models to basically rank the samples from these policies. And then I'm going to say, okay, as I push more and more samples into this ranking process, is the kind of performance I get accurate? And what you see is that, yeah, so orange here is what I'm calling global, or the sort of kind of directly level reward models we talked about earlier. And DPO here is the thing in purple. So DPO does give you some benefit, right? It does better than like 1. But as I sort of get more and more OOD, I generate more and more samples. I don't try to see a huge improvement in performance. The teal line here, the thing that's labeled local over there is basically DPO without the reference. So it's a sort of pi hat MLE we've been talking about. So it really does appear that just going from global trajectory level things to local things just kind of like breaks your OOD generalization without actually, even if you kind of remove the reference policy. The reason I'm making this distinction is that usually people just compare the orange line here to the purple line here, and that's changing two things at once. I'm both adding in regularization and I'm switching from a trajectory level thing to a local thing. Don't worry too much if that distinction didn't make sense, but just trust me when I say that there really is a difference here. Okay. So this seems true. This seems to like give some validity to this hypothesis. But I think you then have to explain, kind of to the point Bart was getting at, why this is true, right? Like, why do these actually generalize better, OOD, right? There has to be some reason, some more fundamental reason why that's true. And I think the first thing that we were sort of surprised to see, we hadn't seen as much in literature, is they also generalize better in distribution. By which I basically mean that if I look at some sort of validation set and I look at the likelihood about how they rank things, you will see the same ordering in terms of in-distribution validation likelihood as you do for out-of-distribution things. And without being too formal, if you have better sort of margins in distribution, you should basically be more robust to perturbations in your data, so you should generalize better out of distribution. And this is sort of like, if you've heard of like SVMs and things like this is why maximizing the margin is used. It turns out that intuition also holds true for deep learning, where basically things that are better classifiers in distribution often generalize better out of distribution. Okay, so you said, okay, if they generalize better OOD, maybe that's explained why they generalize better in distribution, but we haven't explained yet why they generalize better in distribution. And that is what, in the last 9 minutes, we're gonna try and go through. So I'm gonna introduce a term now called a generation verification gap. So if you have taken a CS theory course before, you've probably heard about things like P and NP, right? Anyone tell me what like P and NP are, or why people think they aren't equal?
Here's the problems that you can only solve via brute force, so it takes like exponential non-polynomial time to solve it. And then P is problems where you can solve it in polynomial time.
Exactly, right? So the way I think about it is NP is problems for which we can verify in polynomial time. We can say, given the solution, I can tell you whether it was correct or not in polynomial time. P is problems for which I can give you the solution in the first place in polynomial time. And roughly speaking, polynomial is what computer scientists used to mean efficient, right? So basically, P is problems for which generation is efficient, and NP is problems for which verification is efficient. And generally speaking, people think of like P being some like block here and NP here as being something big. That, you know, if you can verify easily, if you can generate easily, you must be able to verify easily. Now, exactly whether this is true or not is sort of the biggest open question in the field of computer science. So I don't know how to prove that, but most people believe the picture looks something like this. The sort of picture I have in my head for why this is true is something like a Sudoku puzzle. So if I give you the full solution to a Sudoku puzzle, so I give you all the blue numbers, right? It's relatively easy for me to check that this solution is correct, right? I just check, okay, do I have the numbers in each of the columns, each of the rows, each of the squares, right? That's like, you know, like 27 different checks, right? But if I gave you only the black numbers and I asked you to fill all the details in, right? You'd have to basically enumerate every possibility and search over, right? So this is kind of a canonical problem in NP where basically the search problem is sort of exponentially large. It can take a large amount of time. But given the solution, it's easy for me to check, right? So if you've heard of things like 3-SAT or SAT problems more generally, that is basically what, that's basically what Sudoku boils down to. Okay, so there's this sort of idea. And I guess the way I sort of try to remember this stuff is I think of the generation verification gap as basically meaning it's easier to check that I have the right answer than to solve it in the first place. And now I'm going to maybe like complete the picture for you, or what I think is true is that I think for a lot of problems you want to solve in practice for RLHF, they really do have this sort of flavor of a generation verification gap. In the sense that it's easier for me to look at a summary and tell you, okay, this is actually a pretty good summary, than for me to write the summary in the first place, right? It's just why it's easier to grade an assignment rather than for you to actually complete it in the first place. And if that's true, basically it means the picture we had from before is sort of missing a few key parts. So if verification is easier than generation, it also means learning the verifier is easier. So we can roughly think of there being a subclass of the full set of reward models, I'm going to call it RSIM, that sort of contains the sort of, let's say, the ground truth or a pretty good estimate of what the reward function is. Then when we think about the space of policies, right, because of the sort of isomorphisms we talked about, there's some subset of the set of policies, I'm going to call it pi of RSIM, that are policies that are soft optimal for these sort of relatively simple verifiers. And what this means then is kind of end-to-end, when we do RL, we only have to look at this subset of policies, the set of policies that are optimal for relatively simple verifiers, rather than the full set of policies, pi. So really there's a statistical benefit here, in the sense that I've reduced my hypothesis space to just things that look like this. We do more expensive ablations in the paper I linked on the course website, but turns out you can basically ablate away every other change about the difference between generation and verification, and you will always see online algorithms outperform offline algorithms. And it's only when you change that you actually see performance kind of collapse. So the sort of like takeaway lesson here is that you only need to search over this subset of the space of policies in this two-stage procedure, and that makes the problem overall easier. Since I only have to learn this relatively simple thing, and then I just have to throw computation at it to look at this. So I will draw this out slightly more prettily here. But the way I like to think about it, in my head at least, is that we have these policies here as being the generators, the rewards here as being the verifiers. And really what this whole kind of claim I'm making here is that maybe all roads lead to likelihood, right? Like everything is in some sense trying to just maximize likelihood. But R lets us take a shortcut, in the sense that we only have to look at a smaller set of policies rather than all of them. So we are taking a shortcut to the space of policies. We're only looking at policies that are optimal for relatively simple verifiers. So this is maybe the picture you should have in your head. I'm now going to give you two pieces of evidence to close off the lecture. One is that there actually is this sort of gap on the problem we were looking at. And two, when I remove this gap, we see the performance of offline and online algorithms collapse the same thing, matching the information theoretic picture we had at the beginning of the lecture. So to give you some evidence for this, what I'm going to do is the following. I'm basically going to do a scaling study of the size of the reward model compared to the size of the policy. So what I'm doing here is I'm generating samples from a relatively large 7 billion parameter model. And then I'm ranking those samples via models of relatively small 1.4 billion parameter size all the way up to 7 billion. And what you see here, right, is even if my generator is relatively big, using a reward model that's like, I can't do division in my head, but much smaller than the policy, actually doesn't hurt the performance when you think of ranking the samples. And this gives us some intuition that the verifier, the reward function here, is a qualitatively simpler function than the generator here. The thing that checks that if we've done a good summary is a simpler function than the thing that actually generates a good summary in the first place. You also see the reverse being true here, where I can generate samples from my policy, from a relatively small policy, and I can use a way bigger reward model, like a 7 billion parameter reward model, and it doesn't help whatsoever. So basically it's like, okay, I can give you extra parameters, but you don't get anything from them, right? So the function in some sense has to be qualitatively simple. It's captured in this relatively small function class. So hopefully that's some evidence that exists. Maybe to close, I'll note that what we can do is we can actually eliminate the gap in multiple ways, and then you will see the performance of these algorithms collapse together. So my favorite way we did this was the following. If you think of like a contextual bandit problem, like a one-step problem, then rewards and policies, generators and verifiers, must be of the same complexity, because if I give you the score for every arm, it's like a simple argmax for the policy, right? They're very close in complexity. There's some sort of like planning, multi-step decision making required. So what we did was basically try the task of, rather than generating like a 20-word summary, we tried the task of generating like a 2-word summary. So a much shorter thing that's much closer to a contextual bandit, right? Like H basically equals 2. And while online and offline DPO don't collapse to exactly the same performance, they are much closer together than what we saw before. So this is really simplifying down the complexity of the generator of the policy relative to the reward model. You can also do the reverse, where you basically increase the complexity of the reward model. I can take questions about that afterwards if people are curious. But maybe to sort of like give you the final answer here. Really, I think the way we think about RLHF is that the benefit of doing the RL here is really that you only have to search over these policies, these generators, that are optimal for the relatively simple rewards, these verifiers, rather than over all of pi. And this kind of reduction in your search space is really the reason all of this complexity in RL is actually required. So in contrast to what we had talked about in the imitation learning setting, where really the benefit of interaction was you learn to recover from mistakes, you learn to see that you went off the row, you learn how to correct back to the center. Here it's really a statistical benefit, in the sense that I only have to look at policies, not all of them, but just the ones that I know are good for a relatively simple verifier. I think that's all I wanted to say. We're at time, but I'm happy to take any questions afterwards. But yeah, thank you all.